Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review everything covered in week 11. So we're going to go through curve sketching and optimization. So let's start with curve sketching. So when you are asked to sketch a curve, we're only going to look at polynomials, by the way, you need to show these four things. So the first three in green, they can be obtained from using your graphics calculator, so you don't need to show any working for these. But 4 is in a different color. You need to show working as to how you calculate the turning points. So I'm sure you all know what x and y intercepts are, but when we talk about limiting behavior, we're talking about what happens as x gets larger and larger, goes to positive infinity, or it gets smaller and smaller. It gets more and more negative, approaching negative infinity. So this table tells you what happens. It's all about whether the degree of the polynomial is even or odd, and whether a, the leading coefficient, is positive or negative. So I'll explain that more when we graph this function here. So if I want to graph this, the y-intercept is always the value of the constant. Now, because this polynomial doesn't have a constant, the y-intercept will be 0. So I'll mark that. Now we'll find the x-intercepts. Now you can use your graphics calculator to do this, but this one's really easy. To find the x-intercepts, you just let y equal 0, and this one turns out we can factorize pretty easily. And of course, the null factor law says either the first thing equals 0, so that would mean x equals 0, or the second thing equals 0, and that would mean x equals 6. So here at x equals 6 is the second intercept. So now I'll calculate the turning points. Remember, the turning points always occur when the first derivative equals 0. So to differentiate, move the power to the front, decrease the power by 1. So again, I could use polynomial solver on my graphics calculator, but this one is super easy to factorize. So after factorizing, null factor law says either the first thing equals 0 or the second thing equals 0. So there's going to be a turning point here at 0, 0, and there's also going to be a turning point at x equals 4. So we found where the turning points are, but now what we need to do is use the first derivative test to determine whether they are minimum or maximum turning points. So remember, we set up our table like this. We have our two x values of the turning points, and we need to pick points either side. So we take each x value and substitute into the derivative. So if I substitute in x equals -1 into the derivative, that's positive, so the function's increasing at that point or leaning to the right. If I substitute +1 into the derivative, I get a negative number, so the function's decreasing or leaning to the left. If I substitute x equals 5 into the derivative, I get a positive number, so the function's increasing or leaning to the right. So what we found here is that 0, 0, this point here, is a local maximum. So that means that the curve is going to look like this. So we know at x equals 4, there's a turning point. To find the y value, we substitute into the original function here. So it turns out when x equals 4, y equals -32. So this here is going to be the minimum turning point. Now the last thing we need to look at is the limiting behavior. So this polynomial has degree 3, so it's odd degree, and the leading coefficient is 1. A is positive. So it has this situation here. So what this means is as x goes to the right, as x gets larger, y will just keep increasing. So the function will go up like that. We know the function's going to be joined up between these two turning points. What this is telling us is that as x goes to the left, y is going to point downwards. It's going to be decreasing. The y value is going to go to negative infinity like that. So here we are, the graph of y equals x cubed minus 6x squared. Let's now look at some optimization. So optimization is finding the maximum or minimum value, which we already know occurs when the first derivative is equal to 0. Now, sometimes you'll be told to find the maximum or minimum on an interval. In that case, you must check endpoints. So let's look at the function we were just talking about. We want to find the maximum and minimum value on this domain here. So if we call the function y, we already found out that y dash equals 0 when x equals 0 or 4. So remember, when x equals 0, y equals 0. When x equals 4, y is -32. We found that on the previous slide. But the problem is, I found when the first derivative is equal to 0, but these 2 points, they might only be local minimum or local maximum. So what I need to do is check the endpoints. Well, I've already checked x equals 0, so let's substitute in x equals 10 into this equation here. So y would be 1,000 minus 600, which gives us 400. Okay, so what actually happened was, even though we found on the previous slide that 0, 0 was a maximum turning point, it was only a local maximum. This value for y of 0 was only the maximum in the neighborhood around x equals 0. It's not the whole maximum of the function. In fact, this function has no maximum value. But the maximum value on this domain, the maximum y value when x is between 0 and 10 is 400, and the minimum is negative 32. So if you're asked to find the optimal, the maximum and minimum values of a function on an interval, you still find where the first derivative equals 0, but you check the endpoints of that interval in case they give a higher or lower value than at the turning points, because the turning points might only be a local minimum or a local maximum. Let's look at another optimization question. So using the same function we've used on the previous 2 slides, we want to find where the gradient is a minimum. As soon as you're asked to find a minimum or maximum value, you should think optimization when the derivative is equal to 0. Now this talks about the gradient. So the gradient of this function is the first derivative, 3x squared minus 12x. We're being asked to find where this is a minimum. So where this is a minimum is where its derivative equals 0. So we're going to differentiate again. This is the second derivative. That's why I put 2 dashes there. So if I differentiate the gradient function, I get 6x minus 12. So the minimum value of this function here occurs when its derivative equals 0. So clearly 6x minus 12 equals 0 means x equals 2. But this asked us for the point. A point needs an x value and a y value. So I'm going to take my x value and substitute into the original equation. And then I get y equals negative 16. So at the point to negative 16, the gradient is a minimum. So this was the graph of y equals x cubed minus 6x squared. We graphed it on the slide. What it's saying is at this point where x equals 2 to negative 16, this is where the gradient of the tangent is a minimum. If I substitute 2 into this function, I get negative 12. The gradient at this point, if I were to draw a tangent, the gradient is negative 12. So that's where this function is decreasing the fastest. All right, let's now look at a slightly harder problem of optimization. So piece of cardboard, 20 centimeters by 5 centimeters, squares cut out from each corner, folded to make a box. We're going to find the maximum possible volume of the box. Because we're asked to find the maximum of something, straight away you should think optimization, first derivative equals 0. So let's draw a picture of this. So what we're going to do is take this rectangular sheet of cardboard and there's squares cut out of each corner. So each of these bits we kind of fold so it stands up and makes a 3D box. So let's call the side length of each of the squares cut out x. We're going to find the value x that gives us the maximum possible volume. So the base of this box will be 20 minus 2x by 5 minus 2x. That gives us the area of the bottom, and the height of this box is just going to be whatever x is. So the volume is going to be height times length times width. Now we don't know how to differentiate a function in this form, so we're going to need to expand it. So here is a function for volume in terms of x, the side length of the squares cut out. If I want to find where this is a maximum, I need to differentiate it and find where the derivative is equal to 0. So to solve this equals 0, you can just use polynomial solver or the quadratic formula and you get 2 values. So we get x is about 1.16204. The other value, x is about 7.17129. So the reason we got 2 values, it turns out one of them is going to be a maximum and one of them is going to be a minimum. So if we think about 7.17, well, that's problematic because 5 minus 2 times 7.2 would give you something negative. You can't have a negative dimension for a box. So it turns out this one here is not going to be possible. It's actually going to give us the minimum possible value, which it turns out is a negative value and not possible. But if the side length of these squares is about 1.16, if we substitute that here into our original volume equation, we get volume is about 55 centimeters cubed. And it turns out this is going to be a maximum. We don't really need to prove that it's going to be a maximum. We just know this is the maximum possible value obtained using calculus. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.